Here we have a situation where we have an object which is being pulled at an angle. And when you have an object that's pulled at some angle that is not horizontal to your plane or your surface or whatever it may be, you need to analyze this a little bit differently because, as we know, horizontal and vertical components lie in the horizontal and vertical planes. So we have to break them apart. We don't like things at angles like this. So here I have this object being pulled at some angle, and we'll call that angle theta. And we'll go from that, and we'll call this force F. And that is the force that we really care about in this situation. And everything else just kind of plays a role as we're going through, and will come up later on towards the end of this. Now, we would assume that this is a gravitational force, this is a normal force, and some opposing force to our object being pulled may be a frictional force. So we'll call that a frictional force. And go from there. So notice that the object is sliding along a horizontal surface. For the purposes of analyzing the problem then, our x-axis is parallel to the surface and our y-axis is perpendicular to it. So notice that my x-axis is here, my y-axis is here. The applied force of the box can be broken into two components, the force horizontal, or the Fx component, and the force vertical, or the Fy component. So that's actually what I'm going to be doing here. I'm going to take my force F, and I'm going to break it into some force x in the horizontal direction and some force y in the vertical direction. Now, I said earlier that this angle was theta, so we're going to use that as our guide. And we're just going to kind of do some basic trig here. And the force x is the component that is parallel to the surface and is pulls along the surface. So as we can see here, if we do some basic trig and we know F, then F sub x is going to be F cosine theta. And F sub y, or the force that is perpendicular to the surface and pulls the block upwards and away from the surface, is going to be F sine theta. So we know now, based on some basic trig functions, how this force is going to be broken up. Well, the acceleration of the block is parallel to the surface. There is no acceleration perpendicular to the surface since the block remains in contact with the surface during the entire time interval. However, that's not to say that we shouldn't write a Newton's second law equation for both our horizontal and vertical components. And we know that, excuse me, our Newton's second law equation basically, at its most general form, looks like that. A equals the sum of the forces over the mass. And if we do that in the x direction, we would say that this should be the sum of the forces in the x direction divided by the mass. So in this case, I have two forces in my x direction. I have my force x, which is pulling to the right, and I have my frictional force, which is pulling to the left, so is in the opposite direction, so those vectors subtract from one another, and then divided by my mass. So that would be my Newton's second law equation that I would run with if I was attempting to figure out either what the acceleration was, or what the force was in the x direction, or what the frictional force may be, or even what the mass may be if I know other things about this scenario. Okay. The other one that I have is my acceleration in the y direction. Well, again, I'm going to look for my net force in the y direction, and I'm going to use that as my basis for moving forward. Now, when I look at my free body diagram here, I notice that I have my normal force and I have my gravitational force, and those are in opposite directions. But I also have this force y, which is in the same direction as my normal force. So I'm going to say here my force y plus my normal force, because they're in the same direction, and those two together minus my gravitational force, which is in the opposite direction of both my normal force and my force y, and that's all my vertical forces divided by my mass. And that is my Newton's second law equation for my vertical forces. Now, it tells me up here that there is no acceleration perpendicular to the surface. So that means that my acceleration in the y direction is 0. That's essentially what that means when it says there is no acceleration perpendicular to the surface, because my y direction is what's perpendicular to my surface. My parallel to the surface is my x direction in this case. Okay, so now I get a question that's like this. Solve for the normal force exerted by the surface on the block. So I need to use the equation that has the normal force in it, in which case that is this equation, my acceleration in the y direction. So I'm just going to kind of rewrite this, and I don't want to use that one because it's not working. I'm just going to kind of rewrite my equation down here so that I may rearrange it. Now it tells me up here that my acceleration in the y direction is 0, so this is 0. So I'm going to move the mass over here, so I'm going to say 0 times the mass equals Fy plus Fn minus Fg. Well, as we know, anything times 0 is 0, so that's still 0. So 0 equals Fy plus Fn minus Fg. Now, if I wish to solve for my normal force, then I'm going to rearrange and I'm going to move my force y and my Fg to the other side of this equation. So I get my normal force equals Fg minus Fy, which if we think about this and we look at our initial scenario here, I have two forces up and one force down. And if my acceleration vertically is 0, or my acceleration perpendicular to my surface is 0, then that means my net force perpendicular to my surface is 0, which means that these two up forces together need to equal the down force. So if I know the down force and I take away some of the up force, then I know what the other up force is. Okay, so just to review. Going through a problem for an object where it's pulled at an angle, the most important thing to remember is that we need to break that force at an angle into its x and y components using some basic trig, f sine, f cosine, f sine, based on x and y directions and where my angle is. Writing my Newton's second law equations based on what's going on, and then solving for a common problem is solving for the normal force exerted on the surface. And that's a combination of looking at my vectors and going through.